Hey, this is lesson 10.6. We're skipping 10.5 from last year. Um, so this is 10.6. And I want to start by looking at some of the problems from the 10-4 homework assignment. You don't have to pull this out. Let's just look at problems 10, 11, 12, 13. In number 10, notice actually there's a pattern going on in 10, 11, 12, and 13. I wonder if you noticed it while you were doing these problems. But look at the relationship, the quantitative or numerical relationship between the shorter of the two legs in each of these triangles, which has been given to you, and the length of the hypotenuse in each triangle, which has also been given to you. Notice in this first triangle, the short leg here is exactly half of the hypotenuse, or the hypotenuse is twice as much as the short leg. Different way of saying the same thing. And likewise in 11, 12, and 13, the hypotenuse twice as much as the short leg. 6 is 2 times 3, 2 is 2 times 1. Right? And look at how the length of the long leg turned out in each one of those problems. When the short leg was 2 and the hypotenuse was twice as much, the long leg came out to be 2 times radical 3. When the short leg was 5 and the hypotenuse was twice as much, the long leg came out to be 5 radical 3. And you see the pattern here. When the short leg is 3, the long leg is 3 radical 3. And even in number 13, when the short leg is 1, the long leg turned out to be 1 times radical 3, which we don't write as 1 times, we just write as radical 3. So if you notice this along the way, you might have been wondering to yourself, is this an accident? Will this happen every time? Will this pattern continue? What if the short leg is 20? What if it's 100? What if it's a decimal? What if it's a fraction? What if, any number of conditions, would this pattern still hold? Well, it turns out the pattern does hold, but I want to take a few minutes to show you why it holds, where it comes from, because that's what we like to do in high school geometry. So let's go to the lesson for today. These are the notes for today, which maybe you've printed out, maybe you haven't, but there will be a completed version posted for you anyway. Now, in these notes, the question is posed this way: how long is the altitude of an equilateral triangle compared to one of its sides? I don't know that we talked about this word altitude very much in the first semester. We would have if we had been in the classroom. But when you have any sort of triangle, what we mean by the altitude is very much what we mean by the word altitude if, let's say, we're flying in a plane or we're up on top of a mountain. Imagine that this red triangle here is a mountain, okay, and this is sort of ground level. We climb up the mountain out here, but if we want to know what the elevation of this mountaintop is, or at what altitude are we when we're at the top of the mountain, we don't measure the distance from that mountaintop down to the bottom this way. We measure the distance down to ground level at a perpendicular direction to the ground. That's what we mean by altitude, right? If you're flying up in an airplane, okay, and here's the ground, you don't measure your altitude from the airplane this way. You measure it in a perpendicular fashion to the ground, okay? Well, if this is an equilateral triangle, and that's part of the question here, then we know that all of the angles in the equilateral triangle are 60 degrees. So that would be 60 and that would be 60. We also know that all of the sides of an equilateral triangle are congruent to each other. That's just part of the definition. Okay. And we know certainly that this is congruent to itself, right? And so without going into all of the details, what we would have here if we draw an altitude down through an equilateral triangle is two congruent triangles side by side. These angles would be 30 degrees each here, okay? And so if these are congruent triangles, this segment is going to be congruent to this segment. But if it's an equilateral triangle, and let's say I call this segment X, then I would have to call this segment X because they're congruent to each other. And therefore, the length of the entire side of the original equilateral triangle would be 2x. That means that would be 2x, and that would be 2x. And now what I want to do is I want to focus on just 1/2 of this original equilateral triangle. This triangle on the right is what we call in mathematics a 30, 60, 90 right triangle, because its angle measures are 30 degrees, 60 degrees, and 90 degrees. Okay, and notice the pattern that we've already begun to establish here. In any 30, 60, 90 right triangle, the hypotenuse is twice as much as the shorter of the two legs. This is a guarantee. Okay, the hypotenuse is always twice as much as the shorter of the two legs when you know that the angles are 30, 60, and 90 degrees. Well, the original question was, how long is the altitude? How long is this segment right here compared to one of the sides of the equilateral triangle? Or we could even compare it to this segment right here. So I'm going to call that missing side H right now. I could call it any variable I want, but I certainly don't want to call it X or 2X, because it's going to be longer than X for sure. It's going to be shorter than 2X for sure. So the question is, how many X's is it? That's essentially the question I'm asking. Is it 1.5 X's? 1.6, 1.7? How many X's is that hypotenuse? Well, we can use the Pythagorean theorem here to find out, because this 30, 60, 90 triangle is a right triangle, and therefore x squared plus h squared, the sum of the squares of the two legs, has got to be equal to the square of the hypotenuse. So let's solve this equation for h and find out how many x's it is. Well, first I'm going to square the right-hand side. 2x times 2x is 4x squared. Now, if I want to solve for h, I've got to isolate the h. So let's subtract x squared from both sides, and we get h squared is equal to 3x squared. Now, solving for h merely requires taking the square root of both sides, and so we get h is equal to the square root of 3x squared. Well, we've learned how to simplify radical expressions, right? We've learned how to simplify expressions like this, square root of 40, by splitting up 40 into 4 times 10, and then separating that into two separate square roots being multiplied together. Well, let's do that with the 3x squared. Okay? 3x squared is 3 times x squared. Now we can split that up into two separate square roots being multiplied together. So square root of 3 times square root of x squared. And what is the square root of x squared? What do the square root and the square effectively do to each other? They cancel each other out, right? And so h is equal to the square root of 3 times x. But an expression like that on the right, again, we usually like to write the x in front of the square root of 3 so that we don't confuse ourselves into thinking that what has been written here is square root of, and we don't want to confuse ourselves and think, oh wait, is that x supposed to be under the square root symbol or not under the square root symbol? So to eliminate that confusion, we put the x in front of the square root symbol. But essentially what this tells us is that this leg of the 30, 60, 90 is equal to whatever the short leg is times the square root of 3. And this is exactly the result that we saw in those 4 homework problems in a row that we were just looking at the start of this video. Right? So here then is the pattern for all 30, 60, 90 right triangles. First of all, I want you to know that anytime I draw a triangle that is intended to be a 30, 60, 90 right triangle, I'm going to make it look pretty good. I'm going to make it look like the 60-degree angle is larger than the 30-degree angle. I'm going to make it look like between the two legs of the right triangle that one of them is pretty obviously shorter and one of them is pretty obviously longer. And it's always going to be true that the shorter leg is across from the smaller angle, and the larger leg is across from the larger angle. I mean, that's just a truism about triangles. And I'm always going to make it look that way because I don't want to intentionally mislead you. Okay? So in all 30, 60, 90 right triangles, however long the short leg is, the hypotenuse is going to be twice as much, and the long leg is going to be the short leg times x radical 3. So this diagram here is a generalization of how the sides of 30, 60, 90 right triangles all compare to each other. And here is a specific case of one particular 30, 60, 90. Short leg, suppose it's 1. Then the hypotenuse would be exactly 2, and the long leg would be 1 times the square root of 3, which we don't write as 1 times. It's just the square root of 3. So all 30, 60, 90 right triangles fit this pattern, okay? Because think about it, all 30, 60, 90 right triangles would all be similar to each other, right? If we have two triangles, and we learned this just a couple of lessons ago, and we can identify at least 2 pairs of congruent angles, then we know that those triangles are similar to each other. And therefore, all corresponding pairs of side lengths have the same ratio. Okay? So, although I would love it if you recognized and understood and could interpret the meaning of this general pattern, what we're really going to use to our advantage here is the fact that every single 30, 60, 90 triangle is similar to this one. And we're going to find missing lengths of 30, 60, 90 right triangles by knowing that every 30, 60, 90 right triangle is similar to this one. When you do your homework, you want to have this picture right in front of you when you're doing all the homework problems. The next time you take a quiz in this class, you want to have this picture right in front of you while you're taking the quiz. If we were in the classroom, I would require you to memorize this picture, which is not that big of a deal. But since we're not in the classroom, you're certainly going to be able to use it. I mean, even if I said you couldn't use it, how could I stop you from using it? So I'm telling you, use it, okay? Let's go down now and see how we can solve some problems. So we want to find all the missing side lengths in these examples on this page of the notes. The A, the B, the C, the D, and so on, okay? So notice in this first triangle, I've marked a right angle and I've marked a 30-degree angle. So if one angle's 90 and the other one's 30, since all the angles add up to 180 degrees, if we did the arithmetic, we'd find out the missing angle would have to be 60 degrees. So this triangle is a 30, 60, 90, and therefore it must be similar to any other 30, 60, 90. And again, I'm going to use this particular 30, 60, 90 right here. I'm going to draw a copy of that right next to this one. Here's the 30-degree angle. The 60 would be up here. Okay, that 60 would be in there. And I'm going to mark the short leg 1, the hypotenuse 2, and the long leg square root of 3. That's the way it always goes. The short leg is 1, the hypotenuse is 2, the long leg is radical 3. And now to find the length of A, I'm going to use what we learned about similar triangles. All the ratios of corresponding sides must be the same. Now, I like to set up my equations with the variable in the upper left-hand corner of that first fraction. The A corresponds to the square root of 3. And now I need another fraction going from the A triangle to the other triangle. Well, I only have one side length here available to me from the A triangle, and it corresponds to the 1. So there's an equation that now I can solve for A to find the length of A. Well, the algebra here is super easy. Just want to multiply both sides by the square root of 3. That cancels out that square root of 3 there. A is equal to, we don't really need the over 1 in this expression, do we? 5 divided by 1 is just 5, and 5 times radical 3 is 5 radical 3. There's the value of A. And we see again the pattern emerging here, that when the short leg was 5, the long leg turned out to be that short leg times the square root of 3. Okay, let's look at number 2. Once again, I've got a 60 degree and a 90 degree angle already given in this triangle. So I know from arithmetic the remaining angle has to be 30 degrees. This then is a 30, 60, 90 right triangle. So I'm going to draw right alongside it another 30, 60, 90. I'm not going to bother putting in the 30 and the 60 degrees. It's really not necessary. I know I'm drawing a 30, 60, 90 for myself to be similar to this one. Again, the short leg is 1, the hypotenuse is 2, the long leg is radical 3. You have to put these values in the right places. Otherwise, for sure, you're going to get the answer to the question wrong. Okay. Now, here are my correspondences. So I'm going to set up my equation. B over the square root of 3 is equal to 8 radical 3 over 1. Okay. Now, let's solve once again by simply multiplying both sides by a radical 3. That cancels out. We get B is equal to, we don't need the division by 1 again. Okay, we can just sort of discard that. We've got 8 square root of 3 times the square root of 3. Well, you've learned how to simplify that, right? We can multiply the radical 3's together first. Square root of 3 times square root of 3 is square root of 9, which is just the whole number 3. So simplifying, I've got 8 times 3, which is 24. So this B value is 24. Now, some of you may be perfectly okay with that, but some of you might be thinking to yourself, wait a minute. Mr. Nortillo, I thought the long leg of a 30, 60, 90 right triangle always had to be like something radical 3. I mean, didn't you take us through those 4 examples in the homework? Let's go back and look at those. Look, I asked for the long leg. It was 2 radical 3. Asked for the long leg here. It was 5 radical 3. Asked for the long leg here. 3 all these long legs, they all had a radical 3 in them. And now you've come up with an answer to a 30, 60, 90 long leg question, and it's just a whole number? That doesn't seem right. What, shouldn't it be 24 radical 3 or something radical 3? Okay, well, notice I gave you in this 30, 60, 90 right triangle a short leg, which was not a whole number like it was in those homework problems. Okay, I gave you a 30, 60, 90 right triangle, and I declared, look, let's just let the short leg be 8 times the square root of 3. Let's just let it be. Let's just start with that. Okay, here's what I want to make clear to you. These 2 pictures right here do not say to us that the short leg and the hypotenuse of a 30, 60, 90 right triangle are always whole numbers, and that the long leg always has a square root of 3 in its value. That's not what these pictures are telling us. Okay? And I know some students get that in their head, and once it's in their head, they make mistakes repeatedly, and they're completely confused as to why. Okay? These are not telling us the short leg and hypotenuse have to be whole numbers. I can make the short leg of a 30, 60, 90 right triangle be whatever. I can make it a fraction. I can make it a decimal. We could draw a 30, 60, 90 right triangle and have the short leg be 2.5. That's not a whole number. That looks like a 25. 2.5. not a whole number. Okay. And if the short leg does not have to be a whole number, it could be anything. It could be a decimal, could be a fraction, could be a square root. Okay. So do not get it in your head that certain sides of 30, 60, 90 right triangles have to look a certain way. What these pictures are telling us is how the sides compare to each other, but not what any individual side looks like. Okay, so let's go back now to the examples. Third one, this is a 30, 60, 90 because I gave you a 90 and a 30. By arithmetic, the missing angle must be a 60. Let's draw in another one. And the short leg is 1, the hypotenuse is 2, the long leg would be radical 3. Where are my correspondences? C corresponds to the radical 3, 12 corresponds to the 2. So C divided by radical 3 is equal to 12 divided by 2. So this is the first example where we don't have divided by 1 on the right-hand side. That's no big deal. Still, all we have to do to solve this is multiply both sides by square root of 3. And so 12 divided by 2 is 6. And 6 times radical 3 doesn't simplify. It's just 6 radical 3. Okay. Now, the next one has a little bit of a twist to it. But again, I've got a 60-degree angle there and there and a right angle in there. So this is a 30, 60, 90. So let's draw my own 30, 60, 90, put a 1 there and a 2 there and a square root of 3 there. My D corresponds to the 1 and my 9 radical 3 corresponds to the 2. Setting up the equation then, D over 1 is equal to 9 radical 3 over 2. Okay. What do we have to do to solve this for D? You can multiply both sides by 1? Really? I mean, is that even necessary? Come on. D divided by 1 is just D, right? This is already solved for D. We just got to kind of simplify the left-hand side. Can we simplify the right-hand side at all? The answer is no, okay? I mean, don't turn this into a 4.5 radical 3. We generally do not like to do that in mathematics. We don't like to write decimal numbers in front of radical numbers. Leave it like this, okay? There's a kind of an important reason in lessons coming up later this semester why we don't like to write 4.5 radical 3. So please don't. Just, get in the habit of leaving these fractions as fractions. Reduced if possible, always, but not turned into a decimal. Okay? We got 3 more here. And the process is the same for all 3 of these. Process is exactly the same. I'm going to draw my own 30, 60, 90, label the sides properly, 1, 2, and square root of 3, and then here's my correspondences. The E corresponds to this 1, the 9 radical 3 corresponds to this radical 3, so E over 1 is equal to 9 radical 3 over radical 3. Again, solving this really requires no algebra. E over 1 is E, but it does require simplifying this time. The square root of 3 divided by the square root of 3 cancels itself out. Anything divided by itself is 1, right? 6 divided by 6 is 1. Negative 5 divided by negative 5 is 1. You learned this in grade school, okay? In grade school, you were just never asked, what is the square root of 3 divided by the square root of 3? But anything divided by itself, principle you understand, is 1. And so E is equal to 9. Okay? Number 6. Let's see, I'll draw my 30, 60, 90 over here. Short leg is 1, hypotenuse is 2, long leg is radical 3. All right, where are my correspondences? The F corresponds to the 2, and the 12 corresponds to the radical 3. So F over 2 is equal to 12 over radical 3. Solving this for F, or isolating the F, is really simple. Multiply both sides by 2, and we get F is equal to, well, think of this 2 as a 2 over 1. multiply fractions straight across, and we get 24 over radical 3. So we've solved this for f, but this answer is not a simplified radical expression. And I want your answers exact and simplified still, unless I explicitly give you permission to give me, an approximate decimal answer, let's say. All right. So recalling, how do we simplify this? How do we get rid of that radical in the denominator? We multiply by that radical term over itself, which is effectively the number 1, because anything divided by itself is 1. Multiply those fractions straight across, and we get 24 times the square root of 3, and the square root of 3 times the square root of 3. And the denominator is the whole number 3. Don't circle that either, because 24 divided by 3 is 8. And so here, finally, is the simplified exact value for f in this triangle. And once again, I want to point out to you that this was a hypotenuse, and it turned out not to be a whole number, right? I mean, in my specific case of 30, 60, 90s, the one that I always use to solve all of these missing sides, the hypotenuse is the nice whole number 2. But in this triangle, it turned out to not be a whole number. It's got a radical 3 in it. Okay. And then finally, the last one here. Let's see, I'm going to draw a small 30, 60, 90. So I can squeeze it in there. That's 1, that's 2, and that's the square root of 3. Here are my correspondences, g and 2, 16 and radical 3. So g over 2 is equal to 16 over radical 3. Solving or algebra is easy. Multiply both sides by 2, and g is equal to, imagine that's a fraction. Multiply straight across. 16 times 2 is 32. Divided by radical 3. Once again, we don't want to leave the answer with that radical in the denominator. So we're going to multiply by radical 3 over radical 3. Multiplying straight across, we get 32 radical 3 over square root of 3 times square root of 3 is 3. Don't circle that either if you can't, if it's possible to reduce that, but 32 is not divisible by 3. And don't turn it into 10.6 repeating, for crying out loud. Just leave it like that, okay? That's our final answer. Now, let me show you, give you a quick look at the homework. I want you to be alert to some things about the homework. Page 1, every single one of these triangles on page 1 is a 30, 60, 90. We know that because there's a right angle mark in every single triangle, and there's either a 30-degree angle or a 60-degree angle given in every single one of these triangles. So every one of these triangles fits the pattern, and you can solve them the way I just solved all of the examples. Okay? Do you have to write out that specific 30, 60, 90 right triangle with the 1 and the 2 and the square root of 3 in it every single time? No, you don't have to write it out every single time. Okay, just write it out as often as you need to, as many times and as many places as you need to make sure you're getting the correspondences right. Okay, but more so what I wanted to alert you to is page 2. It's another 12 problems, and not all of these triangles are 30, 60, 90s. Okay, like the very first one, look at it. There's a right angle in there. There's no 30-degree angle given and no 60-degree angle given. And so it's not a 30, 60, 90. At which point some students say, well, then how do I solve it? How do you find A? With the Pythagorean theorem. That's how, because I gave you 2 out of the 3 sides. Okay, don't forget, anytime you've got 2 out of 3 sides, you can use the Pythagorean theorem to solve for the third. Okay, so any triangle on this page, which is not a 30, 60, 90, you're going to need the Pythagorean theorem for. All right. And by the way, here's another reason why this first triangle couldn't possibly be a 30, 60, 90, because the 2 legs are exactly the same size, which is not true in 30, 60, 90 right triangles, okay? The second one's got a 90 and a 30 in it, so that's a 30, 60, 90. But this third one does not have a 30 or a 60 degree angle in it. So it's not a 30, 60, 90, and you're going to need the Pythagorean theorem. Notice I'm asking for the exact values and simplified, always, in all of these problems, every last one of them. So please be on your toes about page 2. Don't treat triangles that are not given to be 30, 60, 90s as if they were 30, 60, 90s. Okay? And then on page 3, a couple of more Pythagorean theorem problems, just to keep you in the practice of some of the problems that were among the harder problems from that Pythagorean theorem assignment. Okay? Good luck on the homework. We'll see you next time.